All right, now, we were just finished. That's right. So the stuff we just did was looking at how we get rid of stains, correct? Are you guys awake? All right. So how we get rid of stains. And we worked out that we had to use the idea of like dissolves like, or non-polar chemicals consecutive bond with non-polar, or polar consecutive bond with polar. And we know all the secondary bonding forces. H bonding, dipole-dipole, dispersion, and ion dipole. Okay? Now we're going to add into those 4 secondary bonding forces, we're going to add ion dipole, because that'll come up in a minute when we talk about how soaps work. Alright, I'm going to go in reverse from the way that the text does it. They talk about how soap works, but they don't talk about how we make soap. Okay? So I'm going to go how do you make soap and how it works, or reverse the order. Alright, now, first thing is, in years gone by, I used to have a soap making competition. Haven't done it for a while. We should do it. Yeah, we used to have a soap making competition. The problem is when my hands started to blister, okay, with the sodium hydroxide that students did not rinse out of their soap product, I thought maybe it's not a very good idea to do that anymore. Alright? So maybe we'll bring that in again after you leave. Alright. First thing is, we've already done a section on fats and oils. Okay? We called those, when we talked about them, we call them triglycerides. So at this point in the course, you should be seeing lots of crossovers with stuff we've done before. Okay? For those of you that are concentrating. So you'll see triglycerides, here it is again, and we did triglycerides in the section on organic, okay, when we talked about all the stuff to do with fats and oils. So here we have a fat, alright, and I've chosen that for a reason because soap, most soap structures actually come from a fat molecule, not an oil, okay? But I could equally use an oil that has got a saturated chain somewhere here, at least one saturated point on the chain. I could easily use an oil to make soap as well. So your things like your Dove soaps are based on an oil starting material, whereas the cheapest soaps you'll get, okay, like the cheap, really cheap soaps, okay, the name brand ones, most likely are coming from a fat structure, just animal fat. So you go and get the fat, you boil it with sodium hydroxide, which is caustic soda. We call this, funny enough, alkaline hydrolysis, and we've done it before when we talked about esters. So all we've got here is a triester, and we are breaking the ester, okay, in order to produce back a salt of the carboxylic acid plus the alcohol. Does anybody remember what the alcohol name was called? Glycerol, or propane 1,2,3-triol. So glycerol is always the product of alkaline hydrolysis of a triglyceride. We'll always get glycerol. Alright, now, the compound that we get, this stuff over here, is actually called soap. Alright? Now, if it comes from animal fat is based on an 18 carbon chain, based on stearic acid. You can go back in your textbook and look that up. Here's the structure. Okay, I didn't put all the hydrogens in because there's too many to put in. Okay, so I'll work those out, just complicates it. But if you had to do it like that in the exam, you would put all the hydrogens in, or you would do the stick structure for 18 carbons long. Alright? It has to be accurate. I've just done a squiggly line here, but you would need to do it accurately in the exam. I've just tried to make it simpler, just for our explanation. Alright, so long carbon chain, here it is. So I've just transferred that structure over to here, and it is based on a carboxylate structure, initially from fatty acid. The fatty acid was stearic acid. Alright, so that's the soap structure. But of course it's a sodium salt. So when we put it into water, it dissolves. So really in water, the soap turns into this. It's actually soluble. So floating around in water, I've got a long carbon chain with this very polar, okay, end to the molecule. And you'll see that's referred to in two ways. The polar section is called the hydrophilic, water-loving, and the long section, the long non-polar, is called hydrophobic, or pretty scared of water. Okay? It doesn't want to bond with water at all. Now, this is the fundamental makeup for a soap. It's also the same structure for a detergent. The only difference between a soap and a detergent is that within a detergent, okay, the polar end is a lot more polar than a soap structure. That's number one. And number two, in a detergent, the polar end does not form a precipitate in hard water. So detergents have a distinct advantage over soaps depending on where we're using them and what the application is. So we can also tailor-make a detergent. So if we want a really, really strong detergent, okay, to get rid of all sorts of very, very strong non-polar compounds, we simply have to have a very, very strong or very polar end to the structure, or a very long carbon chain. We can tailor it to whatever we want to get rid of. So you wouldn't be using, for example, the type of detergent you would use to clean off an oil spill on the ocean. You wouldn't be using that on your hands, okay? Because it's going to take away all the oil off the surface of your hands, and it's probably going to be very alkaline and probably take some of your skin off with it. All right? There's detergents and there is detergents, if you know what I mean, depending what the application is. Yeah. And I've done it before. I've actually just got some washing powder, and I've used washing powder to actually get grease off my hands so I can smooth it on the car. And if you do that with washing powder, it goes pretty hot. You know, you just put it on your hands in the powder, put it under the water. Because it's got lots of sodium hydroxide in there as well, it goes very alkaline, and your hands can sting at the end of it. And the stinging is because of the sodium hydroxide taking the top part of your skin off. Anyway, so how does it work? Well, this is supposed to be like a big wash trough or a big washing machine, okay, or a very large beaker, however you want to see it. This is supposed to be a piece of cloth, and this is supposed to be, okay, some stain on the cloth, okay? That could be, and I'm assuming it's an oil stain or a grease stain. Some sort of non-polar stain on the garment I'm trying to get rid of. Now, obviously I need to add to that, I've got to add the detergent. Now, I'm using soap as the example here, but in reality, you probably wouldn't use soap, you'd probably use detergent for this application. But the chemistry is the same. All of these things here, okay, are my soap molecule or my detergent molecule. So it's got a long carbon chain and a polar head to it. Long carbon chain and a polar end to it. Now, you've got to mix the whole thing around because all of these, okay, soap or detergent molecules have to come in contact with the stain. If they don't, it's not going to work very well. So there has to be some sort of agitation within that as well. We've got water, because water provides the medium to move these ions around. Because that's all they are. They're just a big negative ion at the end of the day. Given time, what actually happens is, and I'm not talking about this just one stain being surrounded by these, this is highly magnified. So what I end up with is, over time, the whole container will be covered, or actually it will go almost dark, it will go very dark in colour, almost black sometimes if you're trying to get rid of oil, okay? It'll go this dirty grey colour. Actually, that's what's called grey water, okay? Because it normally is grey, all right? So this eventually disperses, okay? Because what I've done is I've broken up that stain into lots and lots of tiny micelles. This is a micelle, okay? But every single micelle is surrounded by, basically, it's got a negative charge on it. Negative on the outside of all these micelles. Sometimes people seem to think that this thing here is the actual size of what happens in a washing machine. Last I looked, okay, I couldn't actually see any micelles floating around. Not with the naked eye anyway. Alright? So I've got millions of these in the water that's been dispersed through the use of the soap or the detergent. So it's broken the stain off of the garment. Okay, now, this is the micelle. On the outside of the micelle, okay, and I should go back one step actually, but on the inside of the micelle is where we need to start. So we just said all of these things here were the non-polar parts of the stain. So the purple stuff on the inside is non-polar. Matt, need to watch. So the stuff on the inside is non-polar. The non-polar part of the soap or the detergent, the long carbon chain, is attracted to the non-polar part of whatever the stain is. Why? Because, no, like dissolves like is not the answer. Because the non-polar bonds, the non-polar molecules, are attracted towards another non-polar molecules because they have got dispersion forces. So they actually do this. All of these long chains, the long carbon chains, when they get away from the water, the only way they can do it is to go straight to the non-polar compound. But of course, unless it's agitated, the molecules aren't live, they're not going to find their way to that. They've got to come in contact with it. That's why any sort of washing involves some degree of agitation. You've got to move the soap through, okay, through the thing you're trying to clean. Now, at the same time, notice that the outside, and this is not a two-dimensional shape, this is in 3 dimensions, okay? So it's a sphere that I've created. And the whole outside of this structure is negatively charged. So it now looks like one big negative ion sitting in water. But water, we know, is a polar solvent. So the positive, okay, of the hydrogens of the water can ion dipole bond with all the micelles. So what we've actually done is we've actually tricked the water into thinking, all right, that the non-polar chemical is polar. We've actually encased it in a polar shell, and that's the amazing thing I think about that, about how it works. Okay, now it's exactly the same whether it's a detergent or a soap. So if I were able to look at each one of these micelles, billions of which would exist after I actually started to move the stuff around and got things in contact with one another. If I could actually physically take one of those micelles out and look at it, that's how it looks. Now, of course, at this particular point, if I leave the dirty water in contact with the garment, and if the water evaporates, obviously it's going to leave the oil back on the garment. So that's the point where you have to rinse. So you've got to get rid of the water, and as soon as you get rid of the water, gone with it is the non-polar compound we're trying to get rid of. Will?
Wouldn't the negative charges
repel? You're thinking the scenario of silicates?
No, it's not. It's in micelle.
Yeah. Oh, you're talking about on the outside here? Yeah. No, they actually don't, no. Alright? Because the force here is greater than the force of repulsion on the outside of all the negative heads together.
So dispersion is greater than just...
Yeah, it outweighs the negative. And if you went down to that level, if you think about the way that they're probably going to pack on the outside, okay? So I would have probably a CO negative, and then I'd have probably over here a CO, and then I'd have an O negative. Can you see how that's probably going to be spaced out a fair bit as well?
Yeah.
So this is probably going to have some sort of secondary, maybe a dipole bond, but not a very strong one, with a carbonyl. And these negatives are not going to be directly alongside of one another. Unlikely. And even if I bent this down, if I did this, because that's the not, that has to be trigonal planar shape, okay, then it's actually going to be an oxygen, and then a negative, and then an oxygen, then another negative in between. So it's not as if you've actually got a negative right next to a negative, okay? And it's basically, it's not going to, no, it's not enough to repel and break them myself up. But that's good thinking then. All right, any other questions in relation to that? Just to clarify again, we've actually been through this already when we did the silicates and we did the, what are they called? What were the things we used to turn hard water and soft water?
Softeners.
Water softeners. What was the chemical name? Zeolites. Okay. So the zeolites are a structure that turn hard water into software through a process called not zeolitation. We called it cation exchange. Okay. So hard water is not good for soaps because any soap structure, as soon as it comes into either calcium or magnesium, forms a precipitate, and that's the white scummy stuff you get, okay, if you ever washed your hair in soapy water, like with soap. If you were desperate, you'd probably wash it with soap, okay? But it doesn't work very well because eventually it just all falls out. All right, fix. How do we fix the idea of hard water? Well, we either get a water softener, okay, we get a zeolite and we soften the water and then we can still continue to use soap, or, as most people tend to do, we swap over and we actually use a detergent. That's what we actually do. Because these, with Ca+2, they're soluble, okay? They would not form a precipitate at all in the presence of hard water. That's why detergents are much more effective in cleaning than a soap structure. All right, what else was I going to say? Something else. Must have been important. Okay. Any questions about how they work? Nobody got any questions? Okay. All right. Well, then we'll sign off.